Hello everyone, welcome to our virtual KubeCon session. We have an interesting topic today. This is on multi-node jobs with Kubernetes. I'm Madhukar and this will be a joint presentation with my colleague Sanjay Chatterjee. Let's begin. Our work is motivated by applications of deep learning. As we know, deep learning is becoming popular in several areas. For example, in transportation, self-driving cars, medical imaging, smart cities, robotics, and so on. In each of these areas, deep learning is enabling more automation and also adding new value by uncovering more insights. Now, if you look into the AI deep learning stack, there are several layers. The top layer, we have the different applications like computer vision with image classification, natural language processing, recommendation engines, languages, and so on. At the bottom layer, we have the hardware components like GPUs, CPUs, and the various systems that are built using these components. Above them are the architecture-specific libraries like CUDA, Nickel, and so on. Above those are the deep learning frameworks like Tensorflow, Pytorch, etc. Now, for an application to work well, all these layers must function well together. There is a lot of innovation happening in each of the layers. So in this talk, we'll see how to put these things together to work well. So a trend we see in all these applications is that the data is becoming big and models are also increasingly complex and larger. As an example, for natural language processing, BERT is a recent popular model. It began with around 110 million parameters, and BERT large grew to around 330 million parameters. More recent ones are like 8 billion and 17 billion parameters. So for such large models, training them takes a long time, even with a single GPU. Because of this, there's a demand for multi-GPU jobs. As an example, if you look at the graph here, it shows the training time for BERT large using different numbers of GPUs. X-axis is the number of NVIDIA V100 GPUs, and Y-axis is the training time in minutes. So we can see that with 16 GPUs, it takes around 60 hours, that's around 2.5 days. And with 1000 GPUs, it comes down to about an hour. So this speed up is significant because the data scientists can then have a faster turnaround, debug faster, iterate faster, and improve the results. They can also handle larger problems. Similar trend can also be seen in the MLperf training results. So MLperf is a competition where several organizations submit their best training results for popular benchmarks. And even there we see that more GPUs yields faster running times. Now, given the demand for these multi-GPU systems, how do we build them? So here's a sample multi-GPU node from NVIDIA called DGX1. So this has 8 V100 GPUs shown in green here, and they're connected by NVLink within the node. The node has dual socket CPUs and 4 NICs. These are Mellanox EDR NICs capable of about 100 Gbps. So we can run up to an 8 GPU job inside this node using fast NVLink. And if you want to go beyond 8 GPUs, then we can connect multiple nodes together. And we can connect them using InfiniBand or RoCE, which is RDMA over Ethernet. And we do that by connecting these 4 NICs to a connected fabric using different topologies like fat tree, Dragonfly, or other things based on our requirements. So that's the hardware part. Now let's look at the software side. So how do we train these multi-GPU, multi-node systems? So there are two popular approaches, data parallelism and model parallelism. And you can also have a hybrid of these, combining the two. So in this talk, we'll focus on data parallelism. Another important concept with deep learning is that of SGD, stochastic gradient descent. This is where in the backward path of the neural network, we compute gradients and apply them to the weights of the neurons. There are two popular SGD approaches, async and sync. So async SGD is the parameters approach shown here, and sync SGD is the all-reduce approach shown in the figure below. So here the different workers, GPU nodes, they do a computation, and at the end of the cycle, they exchange the gradients in an all-reduce fashion. And that's implemented through NCCL or MPI. NCCL is the NVIDIA Collective Communications Library, and it internally handles NVLink and also InfiniBand RoCE across nodes. So thus it makes use of the fast interconnects. The recent Horovod library from Uber makes it easy to run the all-reduce approach with Tensorflow and Pytorch. So while multi-node is gaining traction, Kubernetes is also becoming increasingly popular to orchestrate these clusters, mainly because of its advantages in ease of management, operations, CI/CD, and then other aspects. However, running multi-node in Kubernetes has multiple challenges. So we divide this into two parts. On the left side, part one is how to get a single multi-node job running end to end. And then the right side is part two, where we look at running multiple multi-node jobs at the same time in a cluster, shared cluster. So let's focus on the left side. And here we look into the end-to-end flow like array jobs, MPI, gang scheduling, and multi-rail RDMA. So towards that, here's a big picture overview of the flow. User submits a multi-node job using a CLI or UI. So that goes to the API server. There's a custom job controller which watches for that and creates an MPI job. And we use the upstream MPI operator from Kubeflow that watches for the MPI jobs and then creates corresponding pods for the MPI job. Those pods are then scheduled by the scheduler using a gang scheduling approach. Once scheduled, the kubelet takes up the pod and tries to run it. So it pulls the container, and the container image has the necessary libraries. It will have framework, TensorFlow, PyTorch, NCCL, MPI, and so on. Once these pods are up and running, they communicate using NCCL on the backend. So that's how the system works. Now let's look at a sample PyTorch job, a BERT job with two nodes, how we would do that. So on the left side, we see a command on node 0, node 1, which is rank 0, and then the command on node 2, which is rank 1. So on both these nodes, we run torch.distributor.launch, and then that starts up 8 processes on the node, 1 on each GPU. And on each GPU, we run the BERT train.py script. That's a single GPU script. So we run that 8 times on node 0 and then node 1. Okay, the master address is set to localhost on rank 0 and IP address of rank 0 on rank 1. So that's how they communicate. So on the right side, we see how we launch the same job using MPI run. So we use MPI run as the launcher, specify the number of replicas, which is the array size, and then it creates that many instances of the torch distributed launch. Okay, so rest all is same as before. So note that we use MPI run as the launcher here, The backend is still nickel. So we manage these MPI jobs using the MPI operator. And for that, I'll hand it over to Sanjay.
Thanks, Madhukar. Hi, I'm Sanjay Chatterjee, and it's great to be presenting at KubeCon Europe 2020 virtual. All right, so we have seen how a multi-node job can be submitted by the user. Now let us look inside the Kubernetes cluster in slightly more detail. Now, typically clusters have many different implementations, different hardware, different stack, etc. So we use the term array jobs as an abstraction for all kinds of multi-node jobs, and users can configure the type and size of the job they want. After an array job is submitted to the cluster, an internal job spec for the cluster is created, and this spec is converted by the control plane components to create the actual K8s pods for a multi-node job. Now we use a component called MPI operator from upstream in Kubeflow, which creates the pods and also manages their lifecycle as a group or gang of pods. Now the pod specs include the setup to handle all the multi-pod job launch, as well as all the node-specific resource requests as shown here. And finally, all the pods belonging to a specific job are gang scheduled by the scheduler to run on the cluster's nodes. Okay, next we'll focus on a few key areas in this flow and see what's going on under the hood. First, let us look at how we enable high-speed networking for multi-node jobs in a Kubernetes cluster. Now, this is an absolutely key requirement for high-performance distributed deep learning applications. We've seen earlier, a single NVIDIA DGX1 node comes equipped with 8 Volta V100 GPUs and 4 100 gig Mellanox RDMA NICs, along with dual 10 gig Ethernet NICs. So when the K8s pod spec requests all these resources, as shown here with the S4 SRIOV RDMA resources and 8 GPUs, we need to make all these available to the pod when it lands on the node. Now, the kubelet is the Kubernetes node agent, and it manages all the allocatable resources on the node for a pod. So to first include the RDMA NICs as kubelet managed resources, we use a SRIOV network device plugin, which will discover the RDMA NICs and register them with the kubelet. All right. So after a pod is bound to a node, the kubelet will start the process of moving the requested network resources from the host namespace to the pod's namespace. And to do this, it invokes the associated CNI plugin. CNI meaning the container network interface. Since the DGX1 node has multiple network interfaces, we use a meta plugin called Multus, which can delegate to multiple other plugins. Now, all of these other plugins can be specific to a different kind of network interface. So we have a SRIOV CNI plugin to configure the RDMA NIC virtual interfaces, and a component called Flannel, which configures the default H0 interface. And both of these are managed by Multus. Okay, the next thing we are going to focus on is the scheduling of array jobs, specifically the gang scheduling aspect of it. We've seen earlier that an array job in Kubernetes will create multiple K8s pods. Now, a further requirement of these pods is to run as a gang, that is an all or none policy, meaning either all the pods belonging to the same multi-node job will get scheduled to run, or none of them can run. Similarly, if one fails, then all of them should fail. Now, this is primarily so that deep learning applications which use the synchronous SGD model we talked about earlier, now they can make progress when they use collectives such as all reduce, broadcast, etc. Now, the default kube scheduler schedules pods one by one. And so if pods from different array jobs get scheduled in an interleave manner, it can lead to deadlocks. So gang scheduling is currently actively discussed in the community. And one proposal is to repeatedly try scheduling the pods. And if that fails, then back off and repeat again. And with this approach, there might be a potential for live lock. So we are experimenting with a different approach, namely using a reservation system for full node pods. Right, so in our approach to gang scheduling, we use something called as a pod groups to be the unit of scheduling for multi-node jobs. Now, pod groups are essentially a logical grouping of pods belonging to a single multi-node job. And currently we only support scheduling full node pods in a multi-node job. So to schedule pod groups, we made some extensions to the default Kubernetes scheduler, which include a new scheduling queue that holds pod groups. That is in addition to the regular pods. We are also experimenting with a new module called the pod group manager, which can reserve full nodes for the pods. Now the node reservations are actually added as a label on the pod, and this allows the main scheduling control loop to bypass the regular pod scheduling and directly bind the pods to its reserved nodes. Okay, now we're going to look at a demo that will actually show the scheduling and end-to-end flow of the multi-node jobs. So here I'm submitting a two-node BERT Pytorch multi-node training job. And we'll see that the job will be creating Kubernetes pods that will be scheduled and will be expected to run on the nodes. So once the job is created, we can look into the cluster and see that the pods are created. And we see that two pods are created, worker 0 and worker 1, with the same job ID, and they are currently in the pending state. So we can look into the pods annotations to look at a queued reason to see why it's pending. And we can see that the reason is resources are unavailable. And if we look at the current state of the queue, we can see there's a number of queue and pods that are in queue. And we can look into the pod spec in more detail to see it's the same command. Eventually, these pods will get to the running state, and then the user can actually look at some real-time telemetry. Some utilization numbers, and with these at real time, they can also look at the status history and some logging as well. Okay, so now let's take a look at the job telemetry in slightly more detail. This is an experimental UI created for some internal users, and it's a very useful tool for them to monitor their jobs in real time. Now, as we can see here, they can see some key metrics from their jobs, such as utilization numbers for GPUs, tensor cores, CPUs, memory PCI links, and so on. And we've built a monitoring and logging pipeline that exports all these node level performance counters and other information to the users so that they can view how their jobs are progressing in real time. Okay, if you remember, we had submitted a BERT multi-node training job in the demo. So here's some throughput scaling numbers from a similar BERT job. And they have two different configurations, phase 1 and phase 2. And they are using some sample training data sets. Now, we know all the performance depends on a number of system and application dependent factors such as batch size per GPU. We have seen that the throughput scaling results, for example, here the sequences per second, have been consistently high in terms of their parallel efficiency. And in this case, we can see that the application can scale close to ideal, even when running on a very large number of GPUs. For example, here on 32 nodes, the job was actually using 256 GPUs concurrently. And mind you, these results are from a shared cluster where multiple other jobs were also running and sharing the cluster network. All right, so now I'm going to hand it back over to Madhukar for the rest of the slides. Thank you.
Thank you, Sanjay. So we now looked at part 1, which shows how to run a single multi-node job end-to-end using the BERT example. Now let's look at part 2. Here, how do we run multiple multi-node jobs at the same time in a shared cluster? And this needs additional features like quotas, time limits, backfilling, etc. So let's see how we handle this. So towards this, we're building a production K8s cluster for multi-node jobs. This is a shared on-prem cluster inside our data centers, and is currently comprised of about 100 DGX nodes arranged in a single hop fashion, and it's being tried out by early internal users. So these are data scientists who are interested in training large models. So if to enable these users to share the cluster efficiently, we enforce quotas. Each user has a default GPU quota of about 32 GPUs, and that determines how many they can use concurrently. It's configurable. We also enforce time limits on jobs, a wall time limit, and also a node hour limit, let's say 128 node hours, which means a 16 node job can run about 8 hours. One key angle with multi-node jobs is that of starvation and backfilling. What this means is, because gang scheduling is non-blocking, there is a large multi-node job, say 32 node job upfront, it can starve for a long time. So to work around that, we enforce a threshold, and beyond the threshold, we start blocking for that job. This can cause low utilization because of idle nodes. So then we backfill the nodes using smaller jobs, shorter jobs. That helps us to improve utilization. So this is a work in progress. We have some initial things in place, but we're looking for more input and feedback to improve that. We also enforce fairness via the DRF score. So DRF stands for Dominant Resource Fairness. It's a popular measure. We also use starvation and age as factors for the job, and we combine all these using a weighted function. So this gives us a dynamic priority for the job, so that the scheduler can use that to decide which job to pick next. For a production cluster, we also need good operations like SRE, CI/CD, and also dashboards and alerts. So here's an example. This is a scheduler and MPI operator dashboard. It shows number of jobs in the queue, how many over quota, how many under quota. It shows scheduling latency, starvation duration, and so on. Even for the MPI operator, it shows latency and other angles. So this is a regular Grafana chart built using Prometheus metrics, and one can build different dashboards like this easily using Grafana. This can be used by the admins and also engineers. We're also trying to enable alerts so that SRE can react to changes quickly. So in summary, we have looked at multi-node clusters with Kubernetes, how to enable that using gang scheduling, MPI, RDMA, etc. So this is a work in progress. As next steps, we are looking to harden these production deployments. Also need to improve performance using storage caching and so on, multi-node clusters. Also looking to add additional array types like MPI, Spark. Also aligning with the upstream framework and so on. So these are work in progress, and we would like to hear from other folks who are trying similar things. One thing I would like to draw attention to is the multi-node enabled containers. So for frameworks like TensorFlow, Pytorch, and also models like BERT, we have multi-node enabled containers. with all the necessary libraries and packages. These are available from ngc.nvidia.com. So we encourage all of you to download it from there and use them. Finally, I would like to acknowledge the contributions of various team members within NVIDIA and also outside. Folks who are working on different layers of the stack, of the deep learning stack. It all comes together. We'd also like to thank KubeCon for giving us this opportunity. Thank you, and we'll now take questions.
So we have a few questions. First one is on whether the telemetry dashboard is open sourced. So the components we are using are open sourced. For example, DCGM, which is Data Center GPU Manager, it exports the different GPU metrics to Prometheus and other components. So that's upstream. And using that in Grafana, one can build different kinds of dashboards. The particular one we are using here is an experimental one that we built for some internal teams. And we're trying to get feedback and see what makes sense, etc. Also looking at the slide here, several of the components we are using are already upstream. For example, the RoCE CNI, MPI operator are already upstream. Also the GPU specific things like device plugin, GPU operator are upstream. So using these, one can start putting together different multi-node solutions. Okay, second question is if we'll be sharing the slides on sched.com. Sure, yes, we'll upload them after this presentation.
Okay.
Also, one thing I think. Also, we'd like to add that if anybody has tried similar things, we would be interested to hear your experience and feedback. So we look forward to discussing with you either now or on Slack offline.
Okay. So I can see a question here. So the question is the gang scheduling code, PGM, open sourced? So as we said earlier in the talk that we have this experimental module called the PodGroup Manager, and we're looking at different aspects of it. Some of the work is currently in progress. Things that we talked about earlier about starvation handling, backfilling, etc. We're trying out different things, looking at seeing what works at scale. And then finally, once we are confident about the code, then we'll go to the next steps, upstream it, and we'll see how that works. Okay. There's another question here. This is about, so the question is, what is the network bandwidth requirements for shared GPU experiments? So a large majority of the multi-node jobs in our clusters are distributed training applications, and they use what Madhukar talked about earlier, the synchronous SGD model. So these applications heavily use collective primitives like all reduce, broadcast, etc. And all of these collective primitives, they require high speed, high bandwidth networks. So our job is to enable these applications to use these high bandwidth networks as easily and transparently as possible. So NVIDIA GPUs, they come equipped with NVLink, and it also supports the nodes. They support GPU direct RDMA across nodes. And to integrate all of this, there's a library called Nickel that we talked about earlier. And so applications can transparently use NVLink and GPU Direct RDMA using Nickel by either using Nickel as part of the application or using a framework like Pytorch or Tensorflow. Overall, I think the network requirements or its utilization depends on many factors like how the application is written. They can either use collectives through Nickel, or they can use some sort of communication and computation overlaps. So applications are, but we have seen that most applications have been able to scale well with very good parallel efficiency on these clusters. So yeah, that's.
So we have another question, which is on comparisons with Volcano. So when we started a few months back, Volcano was still not in a production ready state. And also we had some GPU requirements like working with high-speed networks, RoCE, and so on. And also DGX specific ones like working with full node jobs. So our solution is kind of tailored towards GPU and DGX specific requirements. And that's what we are demoing in production. And yeah, I think so we can now perhaps check with Volcano and see what can be added there and so on. Yeah, one thing we would also add is that as we see on the future work screen, different things need to come together for this to work in production, like the CNI, MPI stuff, and also like efficient storage, being able to download the containers efficiently. So all these things need to work together and hardened in production to have a good cluster. So our goal has been to kind of share our learnings from these things and also learn from the community. Okay, I think we can now close the session and follow up on the Slack channel for discussion. Thank you all for joining.